Hello everyone! We already have one rain shader, so why not add another one? This time it will be based on a slightly more complex algorithm, but it will allow for much more customization and won't suffer from visual artifacts. Let's get to it. Unlike the previous shader, which was based on simple vertical lines, this time we'll try to model the actual shape of a falling raindrop, including its fading trail, which will definitely make our effects more interesting. Enough talk, let's start coding. So as usual, I'll create a new scene, add a color rect as a child node to its root and set its parameters. Let's do it. Right click, create new scene. I'll call it drops because we already have another one called rain, so let's not mix them. And okay, right click, add child node, color rect, and in the inspector we need to set the layout. I usually choose these dimensions, 600 by 400, and material, new shader material, click new shader, and we can call it drops, of course. I'll just put it to the shaders folder and create, and click again to open in the editor. Let's just expand this window a little bit. And as usual, I will delete everything we don't need, so only the fragment function remains in the code. Vertex, delete it, light, delete it as well. Okay, so in the first line, I will assign the UV coordinates of the current pixel to the vector UV. However, this time I will immediately change the sign to minus because, as you might remember from the previous rain effect, if I don't do this, the raindrops would fall upwards, which means we'll do this. Vec2 UV is negative UV. Great. Our effect will be based on a simple principle. We'll divide the screen into vertical columns, and each raindrop will belong to just one of these columns, filling the entire area this way. To make it easier to work with, I'll create a uniform parameter for this purpose and name it density. Uniform float density with a hint range and initial value 100, and the range would be from 1 to, let's say, 500, and the step is 1. Okay, to better see what these columns look like, we can visualize them, but first we need a color that will apply to the resulting raindrops. This will be the second uniform parameter. Uniform vec3 RGB color, which is source color to display the color picker in the inspector, and default value vec3.5, shade of gray. To create the columns, we need to multiply the x coordinate by the value of density and then use the fractional part of the result, which is returned by the fract function. Let's do it. So first multiplication, UVX is multiplied by density, and now the final color would be vector 4, that consists of the color multiplied by fract of UVX, and finally the alpha channel set to 1. Let's wait. Okay. As the default value for density, I used 100, so the columns aren't very prominent. Let's try temporarily lowering it in the inspector. If I set, for instance, 10, now we can see the columns better. Very well. Okay, and we probably have a good idea of where the individual raindrops will be placed. So we can remove the columns and continue with the code, which means I will simply delete this temporary line. For the raindrops to behave as intended, we need to transform the UV coordinates and consider that we want to work with each drop within a specific column and only in the vertical direction. Therefore, we only need the integer part of the new UV value, which is where the floor function comes in. Vector 2, let's call it duv for the drop UV, would be vector 2, and floor function of uvx and uvy remains the same as before. Next, we need to set an offset so that not all the raindrops fall in the same way. To simplify this, the sine function will suffice. Float offset is sine of duv.x. Okay, if the sine function isn't sufficient for our needs, we can replace it with a pseudo-random number generator that I've used many times in previous videos. For now, though, this will suffice and we can move on to defining the raindrop itself. Float drop is fract duv.y plus offset. So we just utilized everything we calculated before to define the very basic shape of the drop. And the result, which is the product of the set color and the value of the drop variable, will be set as the final color of the pixel. Color is vector 4, color, multiplied by drop and 1 as the alpha channel. Okay, as we can see, the result isn't exactly stunning, but we are only at the beginning. These unattractive lines need to be shaped and refined a bit. We'll start with the letter and highlight part of each line to make it resemble a falling raindrop more closely. For this, I will define two additional uniform parameters, which I'll name compression and trail size. The first will affect the distribution of the raindrops, and the second will control the length of the trail behind each raindrop. Let's do it. Uniform float compression with the hint range and initial value 0.2. Let's set hint range to 0.1 to 1 and 0.01 as the step, and the trail size uniform float trail size, again a hint range, and let's start at 50, and the range would be from 5 to 100 and step 0.1. And now for their use. To calculate the fall of the raindrop, I'll create a variable called fall, which will compute using the cosine function with increased frequency to achieve a slightly irregular result. Here after the offset, float fall is cosine of duv.x multiplied by, let's say, 30. Okay, this value will be needed to calculate the trail, which we get as a linear interpolation using the mix function between a sufficiently high value such as 100 and the trail size parameter. So float trail would be mix of, as I said, 100, trail size and fall. Alright, and now we can add all of this into the calculation of the drop value. So we will here increase the fall, it's missing, and the trail will multiply by the trail to cut off some parts of it. Okay, that's looking better, don't you think? The raindrops are still a bit angular, but we'll address their shape shortly. Now, it would be nice if they started moving, so we'll add a speed parameter to control the falling speed. uniform float speed in range and start at point 1, and speed would start from 0.01 to 1, and the step is 0.01 as well. And how to use it? First, I'll add a calculation of position based on the time and speed at the beginning of the fragment function, right here. Float time is internal time multiplied by speed. And now we can multiply the fall variable by this value. So here, time times fall. Okay, as we can see, there are still some minor adjustments needed. First, we want the raindrops and the background to have opposite colors, and also for the color of the raindrops to be more pronounced at their bottom. Both of these requirements can be addressed by using the inverted value, like this. Drop is 1 divided by drop. For now, ignore the fact that some raindrops are flying upwards. We'll filter out this issue soon, but first, we'll shorten the trail using the smooth step function. Drop is smooth step with parameters 0, 1, and drop is the third parameter. Okay, I think we can make it even more prominent by drop multiplied by drop. Great, very well. And now the promised fix for the falling direction of some raindrops. We'll replace the drop value with its sign and multiply the result by the fall value. Drop is sine of drop multiplied by pi multiplied by fall. Okay, this is nice. I multiplied the drop by pi to achieve a greater irregularity in the fall. However, the result is somewhat dark, so we'll introduce a brightness parameter. Uniform float brightness in range, and the initial value let's set to 5, and the range would be from 0.1 to, I think, 10 would be okay. And we'll use it in the calculation. So here sine drop by pi by fall, and here multiplied by brightness. Okay, it's brighter. We are almost done. We just need a small adjustment to the final shape of the raindrop. We'll use the sine function again to achieve a nice shape with a tapering trail. So I'll call it, for example, shape, and it would be sine of fract uvx multiplied by pi to give it nice curves. And now we need to use the shape with the drop, so we simply multiply drop by the shape. And again, I think it could be done even more, shape by a shape. And we have a beautiful result. Now, by adjusting the parameters a bit, we can customize the falling raindrops to meet our requirements and even turn them into a moving star field if desired. Let's start with some customizing. So I will increase the compression and trail size a little bit, change density, and maybe it's too slow. Let's increase the speed. Okay, very cool. Let's just make it shorter to resemble the stars a bit more. And what if we want a horizontal effect? We'll make this small change at the beginning of the fragment function. So UV, let's change it to UV. Now it goes up there, and UV, simply let's switch the coordinates, y, x. Wait for it. This is it. And in that case, the excessive regularity of the trigonometric functions will become more apparent, which we could address using pseudo-random numbers or a noise texture. But we can leave that to the creativity of each programmer. Okay, and one more thing. You have probably noticed that when I was changing the compression parameter, nothing happened. That's because I completely forgot to use it in the code. So it should be right here where we defined the DUV. Let's just multiply that by the compression. Okay, now it has some influence. Let's reset the parameters to its original values, and we can see, maybe I'll just make it falling stars again. Wait a minute. Okay, here it goes. And now if I change the compression, it surely does something. Okay, very nice. And that's all for now. As further improvements, in addition to the mentioned pseudo-random factor, you could color each raindrop differently or make the background transparent instead of black, so you can apply the effect to any texture, as I demonstrated with the previous rain shader. In any case, I'm convinced that the effect has wide applications, and next time I might try converting it to polar coordinates for something a bit different. For now, take care and see you in the next video.